You guys can hear me and the recording, and you guys can see my screen, right?
Correct.
Cool. So, here's the Citrea repo. Citrea is a ZK EVM rollup operating on Bitcoin. What that means is Citrea is using Bitcoin for data availability and settlement. It it achieves this through ordinals like inscriptions for data availability and putting ZK proofs of the rollup execution and then creating a Litecoin proof by reading those proofs from Bitcoin blocks. We can get that Litecoin proof verified in a BitVM instance, specifically in our Clementine bridge, which is a separate repo, by the way. We can do the settlement. So to explain how the repo works and where you can find things, so under the bin directory, we have two binaries, the Citrea binary and the Citrea CLI binary. Citrea CLI binary is usually used for things like backups, restoring from backups, rollbacking DBs, and stuff like that. And in the Citrea binary, so you don't really need these. It's not in the repo. Okay. So under source, you will see, a classic CLI that, you spawn a node on which network with what kind of configs and stuff like that. So this is usually like glue code, except for here where we define which ZK VM elves we're going to be using for each proof and for each network and for each fork. For example, let's see. So for example, on testnet, we're going to be using the same batch proof elf for each fork the testnet has gone through. So yeah, that this file is important in proving sense. Under rollup, we find ourselves kind of defining what kind of DA service we're going to use, what ZK adapter we're going to use. Again, usually glue code here. So there isn't much to talk about. You can either launch a node on Bitcoin or on mockDA, which is like a local SQLite based, mock DA instance. So that's the binaries for you. You can see the past audit reports here. In the guests directory, we have two directories, SP1, which is out of scope, and wish0. So in these guests, there isn't actually much code, you'll see, because these guests actually import code from crates, and these are here for compiling reasons so that I can come here and specifically compile the batch proof elf. So that's guests. Under docs, you'll find a good auditor's guide and smart contract auditor's guide, which you can go into actually, but I can't really share that window. You can go into docs and run this command. Where is it? Here, maybe. Yeah, you can run this shell script to actually build this as an MD book. Yeah. Under resources, you can find things like configs for different networks. There is also like configs for running nodes on your local network. There is configs for testnet and stuff like that. Under Genesis, you can find the Genesis files for each network. Grafana, there is like dashboards. Under guests is compiled ELF files for devnet, testnet, on mainnet, but actually there's a mainnet ELF right now. So there are some scripts which are not that much used. So that's resources for you. We usually do tests and builds out of the make file here. There is also like installing dev tools and installing wish0, commands here. Under docs, you can find like dev setup. It talks about how to set up set up your machine for the repo. Yeah, so that's like the utility directories basically. But the important directories, in my opinion, are under crates. And this is pretty much where 90%, 99% of the code is. You know, we have some in the binary directory, but all of the important stuff goes on here. I've actually made I think, a good explanation on each directory under the address guide, so you can check it out also, like what all directories are and what they're doing. But to explain in this video, so I haven't mentioned this, but Citrea is actually a fork of Sovereign SDK, which is a rollup SDK to build sovereign rollups on any kind of network. We forked a long way ago, and like how things work in this rollup has differentiated a lot from Sovereign SDK, but we're still keeping some of the code, like their database and state management stuff, which you can find under here for the database. And some of the module system we're still using. For example, like the source state, which has the, maybe I shouldn't go into that right now. Okay, maybe I should just go over the directories here and I'll try to dive deep into what's important, all right? So, and things like the rollup interface are also here, which define, you know, your state machine, basically, what your transaction is, what your putting on DA is here, your block struct is here, and there's a few other stuff also that will go later on. So we're still keeping some of the code from Sovereign SDK, basically. So, so in the beginning, we talked about using Bitcoin as DA, and this is where it happens. Under Bitcoin DA create, we define how we're going to store data, arbitrary data on Bitcoin, how we're going to extract it, and how we're going to actually use it in ZK proofs. So if you go to verifier RS, this is what the ZK proofs in our system are using, basically, to show that in a Bitcoin block, there are several transactions that are important to us, and the others we don't really care about. And in these transactions, we can deduce certain data that can be used by other parts of the rollup. So these data are going to be the sequencer commitments and the batch proofs. The sequencer commitments are short commitments to Citrea's latest blocks. And the batch proofs are ZK proofs that show when L2 blocks inside the sequencer commitments are ran, the state goes from A to B, basically. And we put these data on Bitcoin by using functions in the service.rs. You know, this is a DA service used only by the nodes, not ZK circuit, to construct transactions. And those transactions are built here under builders. Let me show maybe, you know, sorry. So in service, let's go to send transaction. The ATX can be a sequencer commitment, a ZK proof, or any batch proof method ID, which we'll go into detail later. And so we send this transactions oh, here. So this queue processes transactions. So let's see. Okay. Create the transactions. So it's calling builders right here. For each type of data we are sending to DA, we have a different Bitcoin transaction builder under body builder RS. Yeah. So those transactions are sent to Bitcoin, and afterwards, like client prover, reads those Bitcoin blocks and uses verifier.rs in a ZK guest to extract and basically show there is a complete list of transactions that are relevant to us and that can be parsed in certain ways, and then that data can be used inside ZK circuits. In order to do that, so it's not feasible to feed in all Bitcoin transactions into the ZK proof and then go over all the transactions trying to parse them by one by one. It's not one by one. It's not feasible. So we have something called inclusion proof and completeness proof, which can be found under here. An inclusion proof is a list of WTX IDs inside the Bitcoin block, a Coinbase transaction, and the Coinbase transactions TX ID miracle proof. So that way you can go over the WTX IDs. We define a relevant transaction as transactions starting with transactions that have WTX IDs starting with certain prefix. You can go over this list, and for any of the relevant transactions, you can expect the transaction body. And if you can verify these inclusion proof against a Bitcoin block header, then you can make sure you're given the complete list of relevant transactions for your rollup. And maybe I can talk about the verifier RS for its other important method, verify header chain. So one of the things you have to do is you have to show that you're operating on a valid Bitcoin header chain. And that's also done by verifier RS. You get a latest DA state known by the circuit, and then you give a block header, and then this function basically checks, if the Bitcoin consensus rules hold up for that header chain. So yeah, that's Bitcoin DA for you. So I come to realize now that maybe we should talk more about the like client proof circuit, or we can go into the other creates in the order that I think makes sense. Jakub, do you have any suggestions right now?
No, I think like we can go ahead with your plan.
Okay. Okay, so since the beginning of this call, I've been mentioning two proofs, like client proof and batch proof, right? So while batch proof, shows that with given L2 blocks signed by the sequencer, the state of the rollup changes. The like client proof extract these proofs from Bitcoin and shows that on a given valid Bitcoin header chain, the valid stress state deduced by batch proofs and sequencer commitments sent to DA would be X, right? And how do we do that is maybe something we can go over right now. So under like client prover, there is circuit. And in the circuit, we define how these rules are going to be working. And the guests directory here actually, for Bitcoin is importing stuff from the directory, right? So whenever you are given a new L1 block, the receiver circuit calls this function with certain parameters and with the new block data, right? So here are the DA transactions, and this is actually your 11 transactions, and you have, so you don't have the inclusion and completeness proof that I was talking about here, because that's actually verified in the guest, I think. No, sorry. Let's see. I didn't see where it was. Okay, we're looking at the wrong function. We should go down to run circuit, sorry. Yeah. Okay. So the circuit calls this function with an instance of DA verifier, an input to the circuit, a storage instance, which is, I think, very smart. I'll come to talk about it later on, and a few other parameters, right? So the like line circuit is like line proof is recursive. So you first, verify the old proof circuit. Sorry, like line proof. I'll say okay. You verify the last like line proof, and then you can use the latest output for verifying the header chain. Again, this calls the DA verifier. And then if you verified this new block to be correct, you can go ahead and extract the relevant transactions from the block. And then you can pass these Bitcoin transactions, which possibly contain sequencer commitments and batch proofs, into this function right here. And this will apply your like client proof logic, which are things like, do I have all the sequencer commitments to verify this batch proof and stuff like that, which I think we don't need to go into detail. The code should be read here. Um, so how does like client proof circuit keep state, um, keep state from proof to proof, right? You cannot be outputting everything and then rereading on the next proof, because that's not scalable. So this tactic is also something used by the batch proof too. What you do is, in this circuit, you output something called the LCP state root. So the circuit is actually keeping track of a jellyfish Merkle tree, and it's reading from that jellyfish Merkle tree by verifying. So jellyfish Merkle tree in short is JMT, verifying JMT inclusion proofs. And whenever the circuit is about to finish, it commits changes and thus creates a new JMT Merkle root. And then this is outputted to be used by the next proof. So that in that way, you can define accessors which read from these jellyfish Merkle tree in certain ways and write in certain ways. So this is the kind of business logic for the like client proof circuit, so I won't go into detail. But I think this is pretty important to understand the Citrea repo. And that happens right here. Under module system, solve state, right? We have two things called the prover storage and ZK storage. So when you are a node, when you are a batch prover or a full node or a like client prover node, you have access to databases on your file systems. So you can read and write to them pretty much anytime. But that's not the case for the ZK circuits, right? They don't really have the notion of storage. The ZK circuit takes in some bytes for the program, some bytes for the input, and then they output something with no access to databases because it's not verifiable. So what we do is, whenever we are running, let's say, an L2 block, or we're simulating the like client proof circuit in one of these nodes, we keep track of state accesses and state writes, and we are accumulating something called the witness. This witness contains things like JMT inclusion proofs, JMT update proofs, and the values. So to give you an example over the like client prover, let's see where this is used, right? So one of the things that the like client prover does is inserting every header, every Bitcoin header's hash into its state. So whenever you have an access to anything inside this repo regarding state, you create something called the working set. Working set is basically like a cache over the database, but in different scenarios, in native execution or in ZK execution, it acts a bit different through the storage instances getting. For example, in insert for block hash, we set certain key to certain value over the working set. If this is called inside the native context, inside node context, like we are going to do here, right? So this process L1 block function right here is actually going and running the circuits L1 block function, run L1 block function in pretty much normal execution environment in your computer, right? Not inside ZK circuit. And it's also passing a storage instance right here, which we call prover storage, as I was showing here, right? Which has access to a database. It's a RuxDB database, by the way. And whenever in this context we are accessing a state over the working set, we are going to be accumulating that inside this witness. And the result will contain the witness itself, right? And this witness, we're going to use that inside the like-line proof circuit input, right? And then inside the circuit, we're going to be using that witness to create our working set. So, okay, in prover storage, you'll see whenever we're getting something from the storage, from the underlying database, we are adding that value to the witness. So we are making a hint. And whenever we are committing, basically, let's see, we accumulate all the inclusion proofs right here. So JMT get proof gives you inclusion proof in the witness again. And whenever we are updating the JMT, we put the update proof and the new root into the witness again. Right? So when I run this run L1 block function at the end, what I'm going to get is a witness full of all the state reads and writes and their JMT proofs in order for the ZK circuit to use. And whenever I'm in ZK mode, right, in ZK context, and I create a working set and I do any inserts and any gets, right, my instance of storage, which is the ZK storage now, is using that witness to get the hints, and whenever I am committing, now I have to use the given given read proofs and verify that the things that were given to me as hints are correct. And whenever I'm committing and trying to construct a new tree, the native proof, the prover storage would have given me an update proof, right here. And now I can verify that too. So in this way, if I have a node and if I know the circuit well, right, I can natively run what the circuit is going to be running, and I can accumulate that witness and then use that in the circuit. So this is both used by the like-line proof and the batch proof. In the like-line proof, it's used for the like-line proof state, and for the batch proof, it's used for the L2 state. Okay. Is everything clear regarding the state access in ZK mode and normal mode? I take that as a yes, and I'll go on now.
Yes, sorry. I missed that you are waiting for a response. Yes, like so far so good.
Okay, thanks. No problem. So since we covered the like client proof state, maybe we can, start talking about the other creates. So we went through the Bitcoin DA. There is the Citrea STF crate, which is actually very small. You are kind of defining your runtime. You know, in Sovereign SDK, there is things called Sol modules, and our runtime has three of them. One is accounts, the other is EVM, and then there is the L2 block rule enforcer. The accounts is pretty much not used a lot. It's used to verify sequencers, knowns for transactions is putting into the L2 blocks. The EVM crate is of course used for EVM related stuff, and then there is the L2 block rule enforcer, which enforces rules like the timestamp rule and block count rule. But one important file here is verifier.rs, which is what the batch proof uses for its logic. In the in this function, and this is called by the batch proof circuit right here. Sorry. All right. What we're doing is we are given a list of it's not actually given, but it's giving as it's giving as the ZK proofs input. We are given a batch proof circuit input, which contains stuff like the initial state roots. These are a little detail, you can read up on them, and a list of sequencer commitments that we're going to be providing L2 blocks for. Part one, where's part two? Okay, part two is it. And L2 blocks for these sequencer commitments, and a few other stuff to actually run those in ZK context. And hopefully, if everything is correct, we'll be outputting all the state roots we've gone through in the sequencer commitments and a few other important stuff, along with the state diff of the rollup. That way, other full nodes, if needed, can reconstruct the state from the L1, basically. Again, anything I talk about, by the way, is under docs. For example, things for the batch proof would be found under the batch proof circuit MD. So you can read from there too. So what this function does in the end is, prepare input, a few checks maybe before, but in the end, it's going to call this function. And this function, asserts a lot of stuff, make sure everything is correct regarding the input, and then keep running the L2 blocks one by one until they're all finished. And then what we're going to do is calculate the final state root and return it. And basically, that's what all the batch proof does. So, okay, that's JSTF for you. The batch prover is what does all the proving for the batch proofs, right? It's a special kind of node which syncs to the L1 and L2, and it's responsible for creating the inputs for these batch proofs, which is not actually an easy process. So there has to be a specific node for it. It wants to do these proofs in parallel. So why do we have actually, right, I can talk about it. Why do we have two proofs? Since ZK proving this kind of EVM execution is not that lightweight, we want to be able to parallelize the proof production process for L2 blocks, right? Every batch proof can run a range of L2 blocks, and no batch proof depends on the other, right? So you can be running, let's say, 1K to 2K in one proof, and in a separate machine, you can be doing 2K to 3K. And it doesn't really matter which order you send these into DA, because the like client proof can verify both of them, and if things work out, it accepts those. Right. So the batch prover wants to prove in parallel. So there's a lot of code around that too here. Yeah, so I don't think there's much to talk about here. Um, so under primitives and common, you can find like utility functions used by every node type. Primitives would be anything that goes into circuits and nodes, and common would be anything that goes into nodes but not into ZK. The Ethereum RPC creates, handles WebSocket subscriptions, some kind of tracing, and some of the fee-related endpoints. And the rest of the RPC functions, I'm going to be showing them under the EVM crate. So I guess one of the most important crates would be the EVM crate, which uses REVM, Alloy, Wrath in conjunction to write as few as possible for EVM handling, right? So we want to make sure, everything is compatible with other node implementations for EVM. So under librs, you'll see a solve module implementation, which defines access to module state, things like accounts for EVM, things for like the balance. Well, actually, the account info has the balance. Anyways, things like the storage, the code for the smart contracts, some configs, and stuff like that, right? So these are all defining access to JMT, basically. So you can go and do, let's see, you can go and do, for example, storage.get. Why can I find it? Yeah, sorry. You can go and do storage.get. So this storage is defined right here. And through the macros, it has a get function, which takes in an input and then the working set, right? This working set was used for the native execution and ZK execution to accumulate witnesses. And here it's also used for getting something over the state for EVM, right? Anyway, so going back to the EVM crate, there's a lot of stuff used here. You'll notice things like config feature native in a lot of places. These define things that won't be running in ZK circuit, because that means like if you're in native context, you're in a node. So these are, for example, accessory states, which won't be proven at all because they're not going to be used by ZK. So under query RS, for example, if you want to implement the EVM get block by number, you're going to be using one of those methods. Let's say self.blocks, which is an accessory state, right? And you can get the last one, for example. So in the query RS file, you'll find a lot of EVM RPC endpoints. So yeah, that's librs again. We are defining like the call for the EVM module. So what happens is the sequencer creates a single EVM module call, which is basically a vector of EVM transactions for that block. And under hooks, we have the sovereign SDKs hooks for that are called be in the beginning of the L2 block, at the end of the L2 block, and while the L2 block is finalizing. This is all node code, by the way. It's not that important. So in between the begin and end hooks, while running the L2 block, we are calling the EVM module right here, which would do some input transformation, and at the end execute these EVM transactions via executor.rs, which is basically making calls to an REVM instance, the classic transacts and commit functions right here if you're into REVM. Yeah, so Citrea EVM is basically using REVM code right here. Yeah. So one notion we have to be aware of is that under EVM, there are some system contracts. So there is the Foundry code base right here, like the bridge or the Bitcoin Light client. I think Bitcoin Light client and bridge are the most important ones. So Bitcoin Light client is used to provide access to the L1 through the EVM context in the EVM context, so that like other smart contracts can also verify transactions in the Bitcoin blocks. This is pretty much populated by the sequencer via things we call system transactions. You can find code related to that under EVM again. And even though it's populated by the sequencer, all the full nodes check that those blocks are known to them also. And inside the batch proofs, we are showing that these edit blocks are valid and they make a complete header chain. And in the batch proofs, we output those hashes, and the light client prover can basically verify that it's a valid header chain. So even though adding those blocks are trusted, at the end they're verified by all participants of the system, so you cannot trick anyone. So since we are running out of time, maybe we can stop with the EVM implementation right here, and we can jump into something called short-headed proofs. So remember, I said like all the hashes are verified by full nodes and the batch proof and light client proof. So that's how it go. So how it's done is through the short-headed proof providers and the short-headed proofs. So let's see. Short-headed proofs are defined for every DA service or DA layer, let's say. And in Bitcoin case, it's a header, a Coinbase transaction, and a Coinbase transaction Merkle proof again, just like the inclusion proof. And it basically does some checks that can be used only to verify the block hash, pre-block hash is given, sorry, verify the block hash, the L1 height, the transactions commitment, and the Coinbase depth. So there is a global instance of either ZK short-headed proof provider or native short-headed proof provider in every node or circuit. Whenever in EVM there is a system transaction, sorry, is it? Sorry. Whenever there is one of those set block info system transactions, find them folder. Set block info. You are calling that global short-headed proof provider to verify that it's a correct. Yeah. Okay, not that one. Okay, so here in verify system key access, right? We're doing a bunch of things, and we are calling the global short-headed proof provider either a ZK provider or a native provider to verify those hashes match, or if not, the L2 block is invalid, we cannot use it. Okay, so that's EVM, and that's short-headed proof provider. Let's go to another crate now. We've done these. So under full node, there is the L2 syncer, and then there is the A block handler. Over the L2 block syncer, we are connecting to the sequencer and downloading blocks and then basically applying them. And in the A block handler, we are tracking L1 for sequencer commitments and batch proofs. And we are tracking the finality of the chain. So under RPC, you'll see last committed height, last proven height, and stuff like that. So we use the DA block handler to, process those commitments and proofs to deduce what the latest state from the perspective of Bitcoin for Citrea, right? So in a way, full nodes don't really run the like client proof circuit, but they know what the state would be in the circuit and in the like client proof through like striking L1. So L2 block rule enforcer is another sovereign module implementation. I won't really go into detail, but it's applying two rules, the block count rule and the timestamp rule. To apply the timestamp rule in full nodes, you can keep track of the last timestamp, but in this case, sorry, sorry for the sound noise. Sorry. To track these in the batch proofs, it has to be done through the state because there is no database, right? So that's how to block rule enforcer. We've gone through the like client prover. So under RISC-0, it's an adapter for RISC-0 ZKVM. So for example, things like ZKVM guests and ZKVM hosts are defined traits so that you can, whenever you want, you can go start using SP1 in the repo. So under RISC-0, you can find stuff related to gluing this trait into the RISC-0 APIs. And in hosts, you can use like RISC-0 Bonsai, or you can locally. There is also one coming for Boundless, which is not merged yet. So under sequencer, you can see sequencer related code. Under runner, that's where we are choosing transactions, producing L2 blocks, and stuff like that. We are also sending the commitments here under commitment service. We are checking out blocks and then, decide to commit or not. If you want to commit, then that sequencer commitment is going to end up in your DA service. Yeah, the sequencer, of course, handles the deposits. There is a deposit data mempool here, and the deposits are also done through system transactions so that it's free. So when you deposit through L1, you don't really need funds on Citrea. It's processed as a system event, so it's free. Another responsibility of the sequencer is choosing the L1 fee rate. So one of the differences of Citrea's EVM, and all of them can be found in this documentation right here, is that Citrea applies L1 fees on EVM transactions based on the state difference the transaction creates. Code related to that can be found under handler. Let's show you some size. So for any transaction is run, you calculate a diff size, and then some kind of discount is applied through some statistics we've deduced from historical Ethereum blocks, so that it's cheaper for everyone. So the sequencer responsible to choose that L1 fee rate. It does so by looking at its Bitcoin node, of course. In like Ethereum rollups, this is not an issue because the Ethereum network has EIP 15159, which sets specific rules for its fee rate. Right, from a block, you can deduce the next block's fee rate, and that enables you to, in some ZK context or anything else, basically to verify fees. But in Bitcoin's case, it's Wild West. You don't really have any rules for fee rates, so somebody has to, choose a fee rate. So the sequencer is responsible for that, but in the future, we hope to, have some rule for that. Anyway, so that's the sequencer for you. We talked about short order provider. SP1 is out of scope. Under star jobs, I don't think it's really somewhere that vulnerabilities can be found. It's like database operations only. Going over to Sovereign SDK again and looking at a few of the important directories and crates there. So under module system, you'll find a few. So we talked about solve state already, but for example, solve modules STF blueprint is also an important crate. Under here, we've shown before the function, the batch proof circuit calls. But for example, for any full node, the apply L2 block function would be applying L2 blocks that they have got from the sequencer. The L2 block is verified here. The hooks are called here. Let's see one of these hooks. So begin L2 block would be calling this function right here, which calls the runtime, defined all the way up in the Citrea SDF. And then, that goes down to the other SAW modules like EVM or L2 block real enforcer. The L2 block hook is not different. We can take a look at the apply L2 block transactions also. The L2 block transactions would be calling, all TXs one by one. No TX can fail. So in our case, like the transaction here, so transaction is not a single EVM transaction. It's a vector of EVM transactions. In a way, Citrea SDF can be Citrea SDF can consist of different modules. Like you can add an SVM module if you want. And a TX here is done by the sequencer that, sends calls to these modules. And for example, in EVM's case, it's a big vector of user EVM transactions, right? So that should be kept in mind. In apply solve TX here, we have a few other hooks, but this dispatch call right here is, what's calling the EVM call function right here. So where is this dispatch call defined is a bit tricky. It's defined, I think, in this macro. I might be wrong, but yeah, under your dispatch call. Yeah. So modules macros might be important also in the eye of an auditor because there's a lot of crazy macros here. Yeah, so that we go over the STF blueprint. The rollup blueprint defines some types for node level things. So these are functions that we were implementing all the way back in the binary Citrea, source rollup. Yeah. So under SAW module score, there is like definitions for the working set, a few caching layers, which are I think are very cool code, by the way. And it might contain very clever vulnerabilities for like tricking state access and whatnot. Yeah, so that's SAW module score. There are a few other SDK related traits here, like the module trait. Under SAW modules API, you can find all the working set implementations, the hook traits. For example, apply L2 block has two. There is the TX hooks, pre-TX and post-TX. So keys is where signatures for solve transactions are implemented. Under module implementations, we now only have solve accounts in solve SDK. Before forking from solve SDK, there used to be a lot of here, but we removed those because we're not using solve SDK as an SDK anymore, as we use it as a part of our code base. Solve accounts, it's simple. Since solve TXs are sequencers TXs, right? It's tracking sequencers nonce for those solve TXs. Right here in pre-dispatch hook, you get the nonce. If sender's nonce is not the same, we return error. Yeah. I guess we looked at a few code in the rollup interface, but we haven't really went into detail. So under rollup interface, so this is not important. We defined like fork managers, some kind of migration. I mean, this is not used code. So like a fork fork has a spec ID and activation height. There's all sorts of code related here. You define some node RPCs and services here also. For example, a DA service trait would be implemented here. Under state machine, I talked about this, you have the L2 header, L2 block, the sovereign transaction types. We have transaction V2 and transaction V1. The reason we have two separate transaction versions is from some finding in this audit report right here. You can read about that. Let's see. Fork node, state machine. Okay. So we have some types regarding the DA here. So for example, data on DA can be complete, aggregate, chunk, batch proof, method ID, or sequencer commitment. We talked about sequencer commitments. So a ZK proof, a batch proof of Citrea can be found on DA in two different formats, either as a complete proof or if the proof is over 400 kilobytes, which is the limit of transaction, size limit of a transaction that you could propagate through the Bitcoin network. But it's not really a consensus rule. You can make a transaction up to 4 megabytes and it would be mined. But the nodes won't really propagate them. So we separate these bigger proofs into chunks and send them SO. And then using a transaction we call aggregates, we show the, verifier or prover where it should pull up these chunks to make the big proof. And the batch proof method ID is used for like forks. It's basically a transaction you send on DA to tell the like client proof circuit to start using a new method ID for verifying batch proofs. So under the ZK directory, you'll see batch proof and like client proof. These are all type definitions. So what's the like client circuit input's going to be? What's its output going to be? So for batch proof, it's the same. You have the versioning. So since batch proof inputs can be very large, we have certain ways to separate it into parts so that we don't really we don't get limited by the ZK VM memory limitations, which used to be much smaller than it is now. It used to be like 190 megabytes for user space, and now it's up to like 3 gigabytes or something. It's crazy. Anyways. Actors into the same test. For example, in a like client test, we define a test with the sequencer, batch prover, like client prover, and a full node. And this test is probably a basic like client proof test, but you can interact with different nodes over the RPC, and you have your Bitcoin DA instance right here. So every test launches a new Bitcoin reg test, so you can test anything. So this can be used for proof of concept, especially things that regard the node behavior. But there's also tests all over the repo, like unit tests or integration tests. Which you can run with make test, or either just go ahead and click run tests, maybe copy these if you need to do some changes or set some environment variables. So yeah, that's the tests for you. Like the main tests can be found here, but also there's tests all around. Let's see, for example, on the EVM, there's quite a bit of tests right here as unit tests. You can also go here and run one of these tests. Yeah. Um, I guess yeah, that covers the whole repo. Do you have any questions, Jakub?
Not for the repo itself, maybe currently, but actually, what are the most important critical impacts from your perspective as a protocol?
Nice question. So I think I've also written about this in the auditor's guide, but I can talk about them, of course, again. So yeah, I'm just curious. Let's see if I've written something like this. Yeah, okay. So under here, I have like obvious and not so obvious, of course, findings. So first and foremost, the most important one would be, loss of user funds. Somebody finds a way to basically steal funds out of any EVM account and they can transfer it to some other address. They maybe even make a withdrawal and they basically run away with the money, right? We don't want that hack like that. Um, since the storage system is not so straightforward, I believe there could be bugs that could, you do some certain operations in some smart contract, but you somehow also, break other contract state somehow. That could happen. Because that's kind of the only part about EVM that we didn't use our EVM because you have to define your own storage relations. Um, we wouldn't. So since the Likeline proof circuit is so important, because it is used by the BitVM instance to basically finalize disputes, it's important that the Likeline proof circuit cannot be halted. Um, so if there is some kind of way to send something over Bitcoin and then the Likeline proof circuit, is halted through some kind of bug. For example, on the security report, you'll see there is a high vulnerability that can break the Likeline proof with a broadly zip bomb. So I forgot to mention, but proof transactions we send to the A, they are broadly compressed to make smaller. So there is things called Broadly bombs, for example. If one was sent to DA, it could break the Likeline proof. One of the most important places would be the bridge smart contract right here. We in-house found a critical vulnerability before in a bridge contract version we've actually published on testnet that allowed for participants to trick the bridge contract. And basically mint Bitcoin, right? So in Genesis, we defined 21 million CBTC at this bridge address. We're not exactly minting and burning, but we're just sending those pre-mined CBTC over to depositors, and you could use that vulnerability to empty out this bridge. I mean, the bridge deposits are right now access guard. So you either need to be the system or the operator EOA to call this function. But it was still a critical in my opinion. Yeah, we talked about halting the Likeline proof contract. We talked about loss of user funds or breaking the storage system. Any EVMTX that's not somehow provable in the batch proof, maybe we missed something and it breaks, would be, not a critical vulnerability because it's not exactly stopping L2 operations, but just finalization. But I think it's a nice finding. For example, in this not so obvious list item, I said any diversion between native L2 block execution versus circuit L2 block execution. So what that means is, since these are two different binary targets, when you think about it, there could be differences in how things are handled, right? If let's say we made some mistake and something, let's say about the storage differs between the node code and the circuit code, and somebody makes a transaction and the state roots are different now, let's say in the circuit and in the nodes, right? That would create a very hard to solve forking situation, unfortunately. So that's a not so obvious attack. So the like-line proof circuit again is built to be deterministic. So given a start Bitcoin state, a start Bitcoin block, and a target Bitcoin block, no matter what kind of inputs you give, right? As long as the inputs are valid, the final result of any run of these like-line proof circuits should be the same. In the past, we've actually uncovered a way for the like-line proof circuit to act differently by ignoring some of these transactions, and that would cause problems because these circuit is built for handling disputes in the bridge, right? You can also read about that, by the way. So I'll keep talking about the bridge circuit and the like-line proof circuit relation. There is also a doc about this, I think should be read. Pretty much anything under these docs should be read by auditors, by the way. Anyways, since the like-line proof circuit is designed to be used by the bridge for handling disputes, if there is a way to make different like-line proof outputs for the same header chain, it's going to just make everything worse, right? There's going to be huge problems. So that's one of the not so obvious things to look out for. So these would be, I guess, like the higher level severities. Of course, if you can trick the full node into accepting an L2 block that's not coming from the sequencer, that could be a case. But since right now we're not using a P2P layer, but the full nodes are talking to an RPC endpoint we're providing, I don't think that's possible. But there is no limits for findings like this, right? Yeah. Does that answer your question well?
Yes, thank you so much. And currently at this stage, I have no further questions. Thank you so much for very detailed explanation of almost every part of the system.
Right. Thank you for listening. So I'll try to be online as much as possible on the Discord server. I can answer questions there also. There is the ping system, I guess, in the Cantina system. I'll try to answer those as fast as possible also. Other than that, we have two other engineers from my team, one from the node software team and one from the contracts team, smart contracts team, to answer any kind of questions. In the Discord channel.